Now we'll take you into a discussion of the ZOS-specific exploitation features that will show up in WASZOS version 8. WASZOS version 8 brings with it a new level of Java which has performance benefits associated with it. The new Z196 processor also brings with it performance benefits. And quite often we see the two combined when talking about WASZOS version 8 performance. So let's step back and try to clarify things a bit by creating a kind of sources of performance framework. Let's start first with the Z196 processor. That machine has a faster chip, larger and better cache, and an out-of-order execution pipeline design, all of which bring improved performance. That's a performance benefit you would see regardless of the level of WAS being run. Let's call this performance category X. The next category of performance is that provided by enhancements in the JVM provided inside of WASZOS version 8. The IBM JVMs are under frequent review and update to improve performance in areas such as the just-in-time compiler, the garbage collection process, and other areas of performance efficiency. The JVM inside of WASZOS version 8 provides such a performance benefit. This is the performance benefit you would see from WASZOS version 8 if you ran it on your existing Z10 processor and compared its performance with WASV7 on the same Z10. Let's call this Y. Finally, there's the performance benefit provided by exploitation of the new instructions in the Z196 processor. These instructions require a JVM that knows about the instructions and exploits them, which is what the JVM inside of WASZOS version 8 does. Let's call this performance category Z. Taken together, the Z196, the Java 6 improvements, and the exploitation of the new instructions, combined it represents the full performance advantage. This is our categories X, Y, and Z added together. At this point, it's necessary to pause and offer a disclaimer. We understand that people are interested in specific numbers related to performance, but we'll not offer those here. Rather, we'll offer a sense for the relative benefits of X compared to Y compared to Z. There are other sources of information regarding specific performance testing that has been conducted. Please consult those for specific test results. Category X is the benefit realized with the new Z196 processor chip. This is a pretty good performance bump by itself. WASZOS customers who acquire a Z196 and remain on WASZOS version 7 for a while longer will see this performance benefit, and it will be noticeable. Category Y is the benefit realized with the improvements in the new Java 6 JVM inside of WASZOS version 8. This provides a pretty good performance bump by itself, so if you're a customer on a Z10 and you move to WAS version 8, you'll see this improvement. Finally, there's the exploitation of the new instruction set in the Z196 processor. This is something we find some eager to assign more benefit than is presently there. So we ask that you understand that right now the performance benefit of this is relatively small compared to the other two categories. But what this represents is an area of exploitation for the future as Java compilers catch up with the new instructions and exploit them more fully. In addition, there's a category of performance not shown on the chart, and that's the performance benefit associated with WAS version 8 itself. As has been true in past releases, general improvements have been made in various areas of the WebSphere product itself. The next category of exploitation involves data resource connectors and a new mechanism for failover. Some of this is common across all platforms, and some is exclusive to ZOS. We should note that there are many elements to availability, and these new features are not the only ones available to you. But these are new, so we'll highlight them here. To explain this new feature, we start with a picture that represents a WAS system with a data connector to a backend DB2. We focus on DB2, though this also works for IMS if you're at the latest maintenance. And there's a WOLA-based variation of this that works with Kix, as you'll see in a minute. We have an application server and an application. The application has a resource reference, which points to a connection factory, which is what provides the definition and mechanism to connect to DB2. A request comes in and works its way back through this system to DB2. This is a very high-level picture of the working as designed scenario. Now let's see what WAS version 8 brings to the table. In WAS version 8, you have the opportunity to define a secondary or alternative connection factory that will be used in the event WAS detects the outage of the primary DB2. On WASZOS, the most common scenario would be this. The primary connection factory is a Type 2 local connection, with the alternative being a Type 4 that provides access via TCP/IP to a DB2 instance on another LPAR. Imagine you lose your local DB2. What happens? WAS detects the loss of the DB2. The connections that existed to that DB2 are lost. But now, WAS version 8 will automatically use the defined alternative connection factory for any new connection requests that come from the application. And if the alternative connection factory is defined to use a network connection to another DB2 on another LPAR, then the application will see connectivity and have access to the data it needs. The application does not need to know about the alternative connection factory. Failover to that is what WAS version 8 provides transparently to the application. What happens when WAS detects that the local DB2 has come back? Connections through the alternative connection factory continue to be used until those connections are released by the application. Any new connection requests are routed back to the primary connection factory. Eventually, all the connections established to the secondary DB2 are released. The connection factory definition is still there, and the new function stands ready in the event the local DB2 is ever lost again. What we showed on the previous chart was function common to WAS version 8 on all platforms. Let's now take a look at how WASZOS version 8 takes this one step further by exploiting specific ZOS functions. We start with the same working as design picture from earlier. Now, imagine that the alternative DB2 is not there, or you've chosen not to employ that option. What else can you do? The first thing is you may elect to have WAS issue a write to operator, or WTO for short, in the event WAS detects the loss of the connected DB2. This is a documented message, so your system automation tools may take over and enact the automation you programmed it to do. The Resource Manager Management Bean is also available, so automation routines may work against that and take whatever action you programmed it to do. The second alternative is to have WASZOS automatically issue the pause listeners command when it detects the loss of the connected DB2. When the listener ports are paused, front-end routing devices no longer see the server as eligible for routing. So if you have a clustered environment, the front-end router will begin routing to the other members in the cluster. One of the limitations of pause listeners is it disables traffic to all applications in the server, which is why we have our third alternative, which is to have WAS stop those applications that are affected by the loss of a connected DB2, but leave unaffected applications up and running. Front-end routing devices such as the IBM WebSphere proxy server and the on-demand router are able to detect the application down but server still up condition and route around that. Stopping just those affected applications is a more granular way to route around the loss of a DB2. WOLA takes advantage of this new function as well. There are a few differences, as we'll see, but in general the same principle applies. That is, when WAS detects that a connected resource manager is lost, take a defined alternative action. If you're interested in more on WOLA, see the WP101490 tech doc at ibm.com/support/techdocs, or go to YouTube and search on WP101490. Once again, we start with a picture of a WAS application server with an application and the WOLA support configured inside, including the WOLA JCA resource adapter. We bring two external address spaces into the picture. For example, imagine these are two CIX regions on the same LPAR as the WAS application server. Imagine further that those CIX regions are routing regions and route to other CIX regions in the sysplex. One of the key principles of WOLA usage is that the external address spaces need to register into the cross-memory services of the application server. That must be in place before any WOLA exchanges may take place, so those registrations are shown on the chart as the orange bars. Now, just like we showed on the previous charts, we may define a primary and alternate connection factory for outbound calls from WAS to the external address space. Imagine the application makes a call. That processes out over the defined resource reference, over the connection factory, and out to the defined resource manager. This is the business as usual working as design picture. Suppose the primary external region goes down. WAS detects that and automatically routes all new connection requests over the alternative connection factory to the second external region. Again, this is all seamless to the application. The application has only one resource reference. WAS is what detects the outage and routes new connection requests over to the secondary connection factory. Eventually, the primary region comes back. WAS detects this and starts routing new connection requests to the primary region. Existing connections to the secondary region remain until they are released by the application. Eventually, all the connections to the secondary clear away, and the primary is once again servicing all the connection traffic. As you can see, this is essentially the same kind of detection and failover mechanism we showed for JDBC and DB2. But here, the connectivity is WOLA, and it works for CIX or external batch programs. This next topic requires we back up and establish a baseline of understanding. Otherwise, the new function we'll describe might not be properly understood. We start with the split JVM model of WASZOS, with a controller region and a servant region, and WLM sitting between the two. The input types come in a variety of flavors: HTTP, IIOP, message-driven bean, and WOLA. An optional function of WASZOS is the ability to provide a classification file to WAS so that inbound requests may be identified and assigned a WLM transaction classification. Imagine a request comes in on the HTTP transport, and the URI on the request is as shown in this example. Then WASZOS will assign the request a WLM transaction classification of, in this example, TC-URI. At that point, WLM recognizes the created enclave as requiring a defined level of service. What takes place after classification is done is covered in quite a bit of detail in the WP101740 document at ibm.com/support/techdocs. We're not going to cover that here because while that's all very interesting, it's not central to the new function in WASZOS version 8 we wish to talk about. What we really needed to do was remind you of this classification file as a way of setting the stage to introduce the new granular reliability, availability, and serviceability, or RAS for short, function in WASZOS version 8. We're not looking to gloss over WLM classification and resource management. It's a fascinating topic and explored in the WP101740 Tech Doc. It's just that it's outside the scope of this video. Okay, now we're ready to introduce the new function in WASZOS version 8. The XML classification file is the starting point for the discussion of the new RAS functions that have been added to WASZOS version 8. Because the new functions are defined and enabled through new definitions supported by the classification XML file. We bring in the WAS server structure we saw before and an XML classification file. This XML file may be scoped to any level. Scoping it to the server level provides you the most granularity. Here's a bit of the XML file so we have a backdrop against which we can discuss the new function. And remember, there are several request types, not just HTTP. Any given classification XML file may be used to classify one, several, or all of the different input types. The URI is what we use to identify an HTTP request. If an HTTP request comes in and matches one of the URI masks, then WAS has a handle on how to classify the request. So what can we do beyond merely WLM transaction classification? WASZOS version 8 provides a new set of supported XML statements to allow greater granularity of control. We'll see those on the next chart. You may specify multiple application identifiers, each with its own set of these new WASZOS version 8 functions. And that brings us to the core of this issue. Before, we could control these things down to the server level at best, and it required a restart of the server to pick up changes. Now it's configurable down to the individual request, and it's dynamically enabled and disabled. Now we're ready to explain what you can do with this new function. Here's a listing of the new functions enabled at the request level. You may now specify dispatch timeout values to the individual request level. If you know certain applications typically have longer delays, you can take that into account, whereas before it was set at best down to the protocol level. Another timeout value is how long a request may wait on the WLM dispatch queue before being dispatched to a servant for execution. Some requests issue their own IIOP requests that go outbound from the server. This timeout value is what's used to determine how long the application waits before that sub-request is considered timed out. The amount of allowed CPU time before the WLM enclave is quiesced is now configurable down to the individual request, as is true of the dispatch progress monitor. You may specify separate dump actions for requests based on the timeout condition that occurs. And you may control SMF 120-9 recording so that records are cut for some requests but not others. And you may indicate if tracing is to be done for a request. A 1 indicates that tracing will be done, and the trace level is that specified for the server itself. This XML file may be dynamically enabled, so that at any time you may activate a new XML file and begin tracing for the requests that have a 1 in this field. You may append a message string of your choosing to all the trace, log, and system messages written for a request. Finally, you may specify what happens when a timeout occurs. Two options are possible: servant and session. Servant results in the familiar EC3 append. Session sends an error back to the client but leaves the servant up and the request continues to run. The MVS modify command allows you to dynamically enable a classification file. The command is as you see on the chart. If you specify a path in a file, then that file is dynamically enabled and made active. You can also tell WAS to reclassify without specifying a file. That causes WAS to just reparse whatever file was in effect before. This gives you the option of either just updating the same file or switching between different files. Using different files gives you a way to back out an XML classification file that introduces behavior you didn't intend. With that, I'll turn this back to Don to wrap up.
Let's summarize and wrap up. Many of you watching this video already have WebSphere Application Server for z/OS version 6.1 or version 7, and you have built up a good inventory of skills related to those levels of WebSphere. Here we're introducing a new version of WebSphere for z/OS, version 8. And one of the key messages we wish to send is that the skills you've acquired with prior versions carry forward to version 8. Version 8 is about refinement on the proven base. We then introduced a series of functions we said enhanced the commonality of WebSphere across platforms. This allows you to leverage your WebSphere skills more fully across all the platforms, including z/OS. Then we brought in some z/OS exclusives in WebSphere version 8. And the first was an updated level of Java that has an enhanced Java virtual machine inside of it. Now, we didn't go into much detail on what's in that new JVM, but we did indicate that the improvements translate to performance gains for WASZOSV8. Then we introduced a new function related to routing to alternative data resources. Some of that function is common across all platforms, and WASZOS added to that by exploiting z/OS facilities and by extending the capabilities to the WebSphere Optimized Local Adapters, or WOLA, function. We finished up with a review of the new capability to make certain reliability, availability, and serviceability functions far more granular, in fact, down to the individual application request level if desired. And we noted how this new function may be enabled dynamically. So in other words, we provided a high-level review of the WebSphere Application Server for z/OS version 8 product, and we set it against a backdrop of a proven base for the product, version-by-version refinements to that base, and an increasing commonality across platforms so valuable skills may be leveraged to their fullest. On behalf of Dave, the WASZOS development staff, and the America's Advanced Technical Skills Organization, permit me to thank you for your continued support and use of WebSphere Application Server for z/OS.